Alright, I'm going to do a video that's going to do a couple sections from chapter 3. So I'm starting in section 3.1 and I just wanted to focus on these two boxes right here that are called equality properties and just go over what they are saying, what they mean. So we have this addition property here of equality, and what it says is if A equals B, then A plus C equals B plus C. So what you're thinking there is if you start with this premise right here, you were able to add a C to both sides. A plus C is going to equal B plus C. And if you have your multiplication, sorry, let me get this still. If you have multiplication, you start with the same thing. If A equals B, you can take a C and multiply it to both sides. So you can take a C and multiply it to A. As long as you multiply B by C, they'll still be equal. You'll end up with an AC equals BC. So I'm gonna go over one of the problems from this section, and we're probably going to be using the equality properties of multiplication and in addition. So I'll come back to that. Then they have this box called more equality properties, reflexive, symmetric, transitive. These kind of seem like no-brainers. If you ever need to state that something is equal to itself and then explain why you did that, then you would say you were using the reflexive property. If you ever had to say that, sometimes I would say what I'm thinking here is that, how usually we have your answer is A equals 5. Okay, well, if you end up with your answer where you have 5 equals A, and that's not how we usually write it, so you want to write it the other way, you're just assuming that's fine, but what makes it fine? The symmetric property makes it fine. So if you end up with you solve your problem, it looks like this, but then you want to change it to make it look like this, you would just have to state your reason why you changed it. It would be the symmetric property. That's what you do in proofs. Every time you make a change, you have to justify it. Why did you do that? And so, anyhow, that's where this one would come in. Over here you have if A equals B, and then B equals C, then A is going to equal C. And you can just see it's a little chain here. And we're going to use that a ton. There's also another property on the next page. Two of them. Okay, the substitution property. If A equals B, then A can replace B in any mathematical statement. We're going to use that one a lot in our proofs. So if you ever know that two things are equal, you can use either one you want. But if you're going to substitute one of them out for the other, your reasoning would be the substitution property. So the equivalence relation is a relation that is reflexive, symmetric, and transitive. So all of those are from the previous box that I just looked at. The trichotomy property, if you have any two numbers, say 7 and 10, exactly one of the following is true. Either 7 equals 10, 7 is greater than 10, or 7 is less than 10. Pick any two numbers that you want, and one of those would have to be true. That's just what happens when you're comparing things. They could be equal. If they're not equal, one is bigger than the other. And, okay, so I wanted to go over this section right here. State the property that happens in each one. So this is just the next page has a longer one, but you could see that right here, you guys should be familiar by this time with the distributive property. So you cover up this for a second and you say, that's what I started with. It turned into this. What justified it? Distributive property. What makes it okay to say 5 times 8 is equal to 8 times 5? The commutative property. X equals 6 and 6 equals y, so x equals y. That follows the transitive property exactly. How can you say that something's equal to itself? Use the reflexive property. So if you needed help with these, study them a little bit. Let me just focus on number 10 for a minute. 3a equals 9. Therefore, 1/3 times 3a equals 1/3 times 9. So if you take a look at this, we used to have one that said if a equals b, right? Then you could multiply the same thing to both sides. So this right here and this right here is what we started with. And what we did is we took these two things and we multiplied both sides by 1/3. There they are originally, but you can see there's a 1/3 in front of it and a 1/3 in front of it. When you do that, you're doing the equality property of multiplication. So it went from A equals B to AC equals BC. You multiplied the same thing on both sides. So what I want to do is take a look at this section right here. And I'm just going to focus right here for a minute and work through these. So you have 5x plus 7 equals 9 times, in parentheses, x minus 5. So take a look at the next, just the next row. Block out everything except for this row right here. What has changed from row A to row B? To me, it looks like the 9 was distributed. Now you have 9x minus 45. So what you have over here is the distributive property. Let's go back over here. You have 5 plus 7, or 5x plus 7. You have minus 5x and plus 45. You have, so let me point out that, okay, here is the original left side, and here is the original right side. So what happens, to the left side, which is right here, we have a minus 5x plus 45. Here's the original right side. We have a minus 5x plus 45. So it looks like we added or subtracted, okay, the same exact things to both sides. When you're doing adding or subtracting, you always call it addition. We don't have a subtraction property. Just, we just have addition properties and multiplication properties. So that's what happens there. So now you have to take this line C and compare it to line D. And right away I see a 5x minus 5x. And it used to be a 5x plus 7, then the minus 5x. So it looks like the 7 and the negative 5x switch spots. Can you see that? This one went here, this one went there. And if we started off over here, it looks like, this minus 45 went here and the 5x went over here. So what do you do when you're changing spots? You should remember now that the commutative property of addition allows you to change spots. That means A plus B equals B plus A. So you can switch their spots. Now what happens between D and E? We have a 0. Well, where does the 0 come from? I don't see a 0, so you got to figure out where they came up with a 0. Well, 5x minus 5x definitely makes a 0. And 7 plus 45 makes 52. And then over here you have the negative 45 and positive 45 equals 0. Combine those to make that. So a couple of things are happening. First of all, I just say you added some numbers. You added those to get 52. And you added these to get your 4x. But the ones that turned into zeros, if you take a look at the description of additive inverses, it will help you figure out that if you take additive inverses, which are basically opposites, and you add them together, you get 0. So now you're going to have to get good at working through each of these lines. So they turn a 0 plus 52 just into a 52. That's the identity property. 0 plus A equals A. All right, they do the same thing over here, identity property. Now, what you want to take a look at is what's happening here. It looks like they're multiplying 1/4 to both sides. That's actually a 52. So they're doing 1/4 times 52 and 1/4 times 4x. So that's the equality property of multiplication. So you work your way through it, and you're always taking the first line and seeing what changed to the next line. Once you figure out what has changed, you figure out what justifies your reasoning for being able to change that. And then that's the property that you do. So this is a proof right here, a step-by-step proof where they let you see what it is that you're supposed to be doing each and every time. And it's going to get a little bit more complicated as we go. Section 3.2 segment measures. The thing that I want to stress in here is just the notation. Okay, AB is a distance. So capital AB is going to be a number. Say like AB could be 7 if it was like 10 minus 3. AB is a 7. I think what I'm trying to stress here is that these two things mean something different, even though they look so similar. This is a line segment. This is actually a piece of a line. That's a piece of a line. And it's the piece of the line that goes from point A over to point B. It's this portion of the line. That's what that means. AB is actually just a number. And it would be the number representing how long this portion is. So it is different, but you do have to memorize those so that you can apply them properly. So we have this definition, another definition of between. And what they have is AM plus MB equals AB. And let me just do that. A, M, and B. In case you need a picture. It says point M is between. Take a look. M is definitely between just by looking at it. You can verify it by saying AM, which is this part, plus MB, so the second part, is equal to the entire part from front to back. So, and then you do want to know that A-M-B means M is between. So this is not true. This is not between. First of all, because A to B is going to be directly right here. That's not even part of our picture, but you wouldn't have the same lengths. If you straighten these out, this part, these two together would end up being longer from here to there. So you know that it's between and basically collinear if the numbers add up. So that's what you wanted to know about these. See how it says, I know you guys have already done this work, but I'm just going to give you some thoughts here. Find a distance. Well, when it says CK, I know that it's not trying to tell me to find CK like that portion of the line. It's asking me to find the distance between those two. Just by notation, you can tell that. All right, segment bisectors. The midpoint of a segment AB is M if M is between, that's what this means, and the distance from A to M and the distance from M to B are equal. So let me use this one up here. All right, M is going to be considered the midpoint if this KM is equal to ML. Let me put that up here. KM equal to ML. Then M is the midpoint. That's how you know it's the midpoint. If it's between, for starters, but you also have to, this portion is equal to that portion. So in your book, you're going to have these proofs that they do for you. And they are going from one line to the next, one line to the next, one line to the next. And every time they write something, they tell you the reason for why it works. So we have this theorem right here called the midpoint theorem. It says if M is the midpoint, then A to M is half of the entire amount. And that should seem, let's do A, B, and M. So if M is the midpoint, so it's perfectly in the middle, then AM is half of the whole thing. That's just what it's saying right here. AM, the distance from A to M, is half of the entire distance. So that's what the midpoint theorem says. And it says you can see there's logical reasoning behind this theorem. Every step has a reason. The reasoning process can be carefully organized into columns. So if you're wanting to prove something, first of all, you decide that it's what you make a statement. So you have M is the midpoint because they're saying if M is the midpoint. So you assume that's true, and you're going to see if you can come up with this end. So if M is the midpoint, then AM is half of AB. So start off with just stating M is the midpoint, and that's just something that's given. So AM equals MB, and AM, or sorry, M is between A and B. So how are you able to say that AM is equal to MB? Why are you able to say AM is equal to MB? So far, all you've said is M is the midpoint. So if you turn over, okay, I missed it. I guess that is the one we're using. Okay, it's right here. I missed it. Okay, if you know something's the midpoint, M is the midpoint of AB, then you know that AM is equal to MB. So down here, when they said M is the midpoint, you're able to say that AM is equal to MB. All right, so now you go from AM plus MB equals AB. So, all right, so how do you say that AM equals MB and change it to the next line? Well, if you take a look, just go back 2 pages at the definition of between. All right, if M is between A and B, then you can write AM plus MB equals AB. So that's what they used over here. They were able to write that. Now you have AM plus AM equals AB. These two lines look identical, except for this one said MB and this one says AM. Why are you able to substitute these out for each other? Earlier on, you were able to say they were equal. The substitution property says that anytime you have something that's equal, you can substitute one for the other. All right? This next line went from AM plus AM, and it changed itself into 2AM. Well, how do you do that? The distributive property. Or I would say adding. But adding comes from the distributive property. How do you have 2 times AM and AB, and now all of a sudden you have AM and half of AB? It looks like you multiplied both sides by 1/2. If you multiply this side by 1/2, it turns into that. Multiply AB by 1/2, it turns into that. So it's the multiplication property of equality. So you started off with M is the midpoint of segment AB. Now you have AM is equal to half of AB. This is, I'm not expecting you guys to know this. I just want you to start seeing it and reading through it and try to follow along. Every time you see these done for you, you want to follow along and see if you can figure them out. These are going to be useful for you in the future. You will end up doing them on your own, which is the hard part of geometry, but it really doesn't start until I'd say the second half of geometry. So the bisector of a segment is a curve that intersects a segment only at the midpoint. I thought that kind of made sense. Bisector means it's going to cut it in half. Congruent segments are segments that have the same length, and this is a new symbol for you. Congruent is an equal sign, I hope it's going to focus, an equal sign with a squiggle on top. That's congruent segments, but congruent segments are segments that have the same length. So, is CD congruent to EF? Remember, if you don't have a line over it, you're asking about the distances. So CD is 6 and EF is 6. So you work it out. They had CD is equal to EF. Therefore, you can put CD is congruent to EF, and it's a segment. Correct notation is very important in geometry. Get into the habit of learning and using correct notation. Perimeters. Oh, let me see. Yeah. Let's go with it. Perimeter is the distance around a closed curve. You add these up. What happens if you have a perimeter of a regular n-gon? If you remember what regular means, it means that all the sides are the same. So if you have so if you have an octagon, okay, N, when it says n-gon, it means 8-sided polygon. So if you have 8, plug in right here, and S is just your side length. If you have an octagon and every side is 3 units long, you just take 8 times 3, and you could do a quick perimeter, which is 24. When you start working with circles, the perimeter of a circle is something you call a circumference. One of the things that's kind of interesting here is that if you want to know what the circumference is, the distance around that circle right there, you could see that if it was wrapped with a wrapper that went all the way around, if you unwrapped it, you could just measure the edge here from here to here. And if you saw how long this was, you would know that's how long this is, because it came from directly around it. So circumference is the distance around a circle. Here's the formula, C equals 2 pi r. I wanted to point these out over here. There's two ways of writing it. C equals 2 pi r. R is a radius. And if you remember, a radius is basically, let me squeeze it right here, from the center to the side. If you can recall what a diameter is, a diameter goes all the way across. Whoops, straight though. So a radius, 2 radius is equal to 1 diameter. When you know that, you can take this 2 and r, the 2 radius, and substitute it in for a diameter. So you also have C equals pi times diameter. Whoops. And so that's what you have right here. C equals pi d. C equals pi d written right here. But you could also, if you're working more with radii, go ahead and use that one. So that's section 3.4. I just want to go over the ones that we've done so far. Section 3.5 is going to be a new one. Polygons inscribed and polygons circumscribed. I'm going to do a separate video for that. So 3.1 through 3.4 is some of the stuff you guys have already done, but this video needed to be watched, and just to touch up on the things that weren't worth making a video all by themselves.